I'd like to introduce our speaker for the evening. So we already heard from Don earlier, but Don is giving us a talk called The End or How I Learned to Stop Worrying About the Apocalypse. And I think that title is amazing. So I look forward to hearing it. Thank you so much, Don. Take it away.
All right. Thanks a lot. I'm going to share a screen here, and I'll ask that you please keep yourself muted, and I'm not going to turn on my camera to save bandwidth, and hopefully everyone here will be able to see my presentation there. So if you got any questions or anything, type in the chat. I'll try to take questions at the end, so folks can unmute themselves then. So, well, we were just mentioning about the pandemic and stuff, and it's a little bit relevant to what I'm going to talk about tonight in a sense. Because about this time last year, we were in the early stages of the COVID-19 pandemic, and there were those who believed this was going to become an apocalyptic kind of plague. Of course, there were others who didn't take it seriously at all. But here we are a little over a year later, and it's clear to see that both sides of the debate had a lot about what was going to happen wrong. However, the Chicken Littles did have some things that weren't too far off the mark. It was pretty bad, and still in many parts of the world is bad. And for us, it could have been a lot worse. Something like this could turn out to be a civilization-ending kind of event if left unchecked. But anyways, this epidemic rekindled my interest in apocalyptic stories. And as I reflect back on my naive and religious youth, at that time I got caught up in end-time prophecies and stuff like that. But later I became skeptical of it all, as a lot of those weird predictions failed to come to pass. And at that point, I stopped focusing so much on endings or the end of the world and things like that, and just lived life by the moment, and then every day as it came. Recent events show that how close we can really come to the end as a species if we're not careful. So I began to ask myself, what does science really have to say about the end of the world? And this talk is a reflection of the journey I made in exploring that question about the end of everything and how I learned to love it. So shall we begin? First, I'll start with what this talk is not about. The kinds of endings that I'm not going to be talking about, these are possible endings that wouldn't necessarily be world ending, rather they would be civilization ending. And they range from low probability to the ridiculous. Some examples include human-induced apocalypses, such as, ABC War or NBC War. I don't mean like network or the Battle of the Network Stars, although if you remember that and if you enjoy seeing like William Shatner in short shorts, you can find old episodes of it on YouTube. No, I mean atomic, biological, chemical warfare, or more commonly known as NBC, nuclear, biological, and chemical warfare. So I won't be talking about that. Anyone remember what this is from? I'm also not going to be talking about anthropomorphic climate change, something very real and something very challenging to us, and it could lead to serious problems for our civilization. It's not so much about how it affects nature as it affects us. It is very real, and it's going to be very costly to us down the road unless we do something serious about it. Or other forms of civilization events I'm not going to be talking about, economic collapse, doomsday machines, stuff like that. Or something called the technological singularity. This is something that was speculated about a long time ago, and I've heard it talked about again recently. And there's some versions of it that are somewhat apocalyptic. An example would say that eventually there's so much information out there on the internet that you search and can't find anything. I mean, it's almost getting that way now. You go to Google and you have to sort through a lot of nonsense to find things you really want to find. And some say that the internet is a kind of singularity that we're in right now. If you're a sci-fi fan, this is a good series that I've read. It's military sci-fi, but it also delves a little bit into this idea of the technological singularity and the effects of it. But it's a good series. I recommend it. I'm not going to talk about natural human extinction, things like declining birth rates and disease, things like that can lead to eventually the collapse of of human civilization or our extinction as a species. I'm not going to talk about alien invasion, very speculative stuff like that, or supernatural apocalypses. Nope, sorry, not going to be talking about that stuff either. Um, the things I'm going to be talking about, well, it's going to be in two parts, this talk. Essentially, one part's going to be about the end of the world or the end of Earth, things that could, end our planet, and the end of everything, the end of the universe. Um, I'm only going to be considering likely events. And when it comes to things like this, there are really four kinds of probabilities. There are, and the four types are called theoretical, empirical, subjective, and axiomatic. All right. Now, what the difference between them is, theoretical is most what we learn in school, like the odds of a dice coming up with a certain result, etc. Empirical covers, how probable after a specific number of tries a number will come up. Say you roll dice so many times until the number 6 comes up. Subjective is basically someone's individual measure of it, kind of guessing or estimating how probable an event is. It's more based off feelings or gut feelings or things like that. Axiomatic is a kind of a unifying principle as to what conditions subjective probabilities can apply to theoretical or empirical probabilities. So human-induced apocalypses tend to fall under the subjective category as far as how likely nuclear war is and things like that. And these, again, generally only lead to civilization-ending events in that regard. The most likely scenarios are actually pretty much all astronomical in nature. And the probability approaches unity at very large time scales. What does that mean? That's science talk. That means they basically, the longer of time period you wait, the certainty becomes pretty much 100% of these events occurring. So over like scales of millions or billions of years. Well, strangely, to talk about the ending, I really need to start at the beginning. All right. And I'm going to be covering a lot of stuff here, glossing over a lot of history. So forgive me if I skip some relevant detail or something like that you happen to know. I'm just giving kind of an overview here, overview picture to give you a sense of where we are and help us get to the place where we can theorize about the end. Okay. Before the Enlightenment, pretty much all ideas of the creation of the world were supernatural in nature. Everything from Western beliefs in an Earth about the same age as human history, to Hindu beliefs about the creation universe, its death and rebirth in an ongoing cycle. As the scientific revolution progressed in the 18th and 19th centuries, it became clear that young Earth creationism and other special kinds of creationists really weren't correct. In particular, people like Charles Darwin here and Charles Lyell and others show that creation was not needed to explain the origin of life and the geology of the Earth. Indeed, you can even consider Charles Darwin here on par with Newton and Einstein when it comes to the greatest scientific minds of the Enlightenment, by the way. But they generally started to become interested in how things started in the age of the Earth and things of that nature, and how it came to be. However, these gentlemen and many others set about, when they set about to show the age of the Earth, and they, using at that time advancing techniques of dating and things like that, there was a glaringly big problem before them, though, and that was questions about the sun. Determining how old the sun was. Most either assumed the sun was as old as the Earth, or they tried to use what was known at the time about the only field of science that could possibly answer this question and explain how the sun produced so much energy, chemistry. Some thought the sun was literally burning. In this hypothesis, the sun was a large chunk of burning coal, and calculations showed that it would only last about 5,000 years. And that would fit with special creation myths, but it didn't really match up with the geologic dating of the Earth. Many other scientists attempted to explain the energy production of the sun and thus determine its age by assuming, say, it was bombarded by meteorites was one idea. And they also found ages that, using this technique, that were much younger than the accepted age of the Earth at the time. So scientists such as Lord Kelvin here argued that the sun was undergoing gravitational contraction. And using this as a basis, he calculated the Earth to be roughly on the order of 20 to 100 million years old or so. But this was still much younger than the estimated 250 to 500 million year age estimate by geologists at the time. Even the discovery of radioactive decay didn't answer the question and provide the energy necessary to help, and also to help date the sun. All it did was actually make age estimates of the Earth even older. And it really wasn't until the 20th century that the answer was found. A guy named Hans Bothe, Hans Bothe, in his theory of nuclear fusion, that he was able to explain the energy production of the sun and eventually determine its age at about 4.5 billion years. And then modern radiometric dating of meteorites put the Earth at about a slightly younger 4.45 billion years or so, and life arising about 500 million years later. So, but then we move into the 20th century, and as observational science improved, one of the ideas that started to take hold at the time was something called steady state theory. And in this hypothesis, the universe is eternal. No need for special creation in the universe because it was always here and always would be. No need for divine retribution to bring about its end. And even though it was becoming clear that stars and their attending planets would die at some point, the universe kept renewing itself. Matter was continuously being created. Even though this idea did violate the laws of thermodynamics, scientists were confident they would be able to find an answer eventually to save those laws. So where does that put us in our understanding about the beginning of the world, the formation of the planet? Well, we turn to a somewhat older idea, first postulated by Immanuel Kant and Pierre-Simon Marquis de Laplace, what's called Kant-Laplace theory. And they hypothesized the planets actually condensed out of the sun's atmosphere. The modern version of this, backed up by observation, is that in these large nebula, you have clumps of gas that contract under gravity, and they'll have some slight angular momentum to them. In other words, the atoms in the gas are moving, even though they're moving randomly, they'll generally be moving in one direction versus another, and that'll set about a rotation that eventually flattens the ball of gas out into a disk. And in the disk, the planets will further contract and form. Thus, like our solar system, the planets all orbit in the same plane, going generally the same direction around our star, the sun, and has been found in most other cases with extrasolar planets, the same thing, that they generally are all in the same plane, orbiting stars in the same general direction. So that's where we are now. So you might be asking yourself, okay, that's great to know, but how will it all end really? What does this have to do with the end? Well, considering the scientists of the time, they weren't bothering themselves too much with the end of the universe because, again, most of them held the steady state model as the dominant model of the universe. They did begin to focus on the end of the world, however, and they felt, though, that if the world was going to end, it most likely would be because of ourselves and the super weapons of our own creation, i.e., like the atomic bomb that was created at the end of World War II. So man-made doomsday became an all too real possibility. And science had basically created the means of our own destruction. Is this the whole story, though? Well, as I said at the beginning, I'm not going to bother with the possibility of human-induced apocalypses. But there were scientists at the time who did begin to look at other, more natural ways that the world could end. So, what are these likely world-ending scenarios that can happen? Well, probably the first one that comes to mind for most folks is impacts. Large asteroids, comets, things of that nature. The most famous that most people know about was the impact that wiped out the dinosaurs 65 million years ago. Um, it was discovered there was a layer of rock that dates around this geologic time that was enriched with an element called iridium. That's very rare near Earth's crust, but is very common in asteroids and meteorites that have been found. And so it was assumed there was some kind of large impact because this layer was found pretty much around the world. And later on, there was a crater found that dated geologically roughly from around the same time. So we're fairly certain that it was this large impact that wiped out the dinosaurs. And again, it was dated about 65 million years ago. Now we do have organizations such as NASA. It's operating programs. An example is their Near Earth Object Program that are looking for things that could impact and do harm to the planet and probably even wipe us out, things like that. And they are fairly confident they've completed about a 90% survey of all the large objects that could possibly pose any problems to us. And the probability of something impacting us in the next century or so is actually pretty low, based off that data. But we do actually get hit quite often, and actually we get hit every day by something. And usually these are in form of micrometeorites and small rocks and dust that make, when you go outside at night, on a good clear night, dark skies, you look up, you occasionally see a meteor. We term these sporadic meteors. There's random, not necessarily associated with a meteor shower or anything like that. But that's basically this debris that we're plowing through as we orbit the sun. And because of the Earth actually gains hundreds of tons of mass every day. I might take a quick break. So it just depends on the size of the object, how often we basically impact it. Now, anyone remember this movie? The impact in this case, world ending, wasn't even really civilization ending. It did do a lot of damage to the planet. And there have been quite a few of these kind of meteor impact movies out there. One of them is quite terrible and won't be mentioned. But out of all of them, I believe this is the best one. If the topic interests you and you want to see a decent movie about it, this would be a good movie to watch. Very large impacts, though, would be very devastating if they actually occurred. Now, the probability of something like this case, this is what would happen if the dwarf planet Ceres impacted with the Earth. Ceres is the largest, was for a long time considered the largest asteroid. Now it's termed as a dwarf planet. And what would happen if it impacted the Earth? It literally would turn the entire surface of the planet molten, and nothing would survive. So this would be a very devastating event. But the chances of this happening are very, 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 very remote. It was more likely early in the solar system that large impacts like this would and actually did occur. There was one such impact of a body about the size of Mars that formed the moon early in our history. So without this large impact, we wouldn't have a moon. We'd be a lot more like Venus or Mars that don't have large satellites. But again, the probability of something like this is very, 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 very remote over the lifetime of the solar system. So no need to worry about it, mark your calendars or anything like that. Another possibility are giant solar flares. Our star is very active, and it's a middle-aged star. In fact, as I mentioned earlier when I was announcing about our sun programs, we're starting to go into a period of higher activity called solar maximum over the next few years. Sun's going to ramp up its activity, have more spots, more flares, things like that. But as a middle-aged star that rotates rather slowly, the the chances of it producing a flare large enough to do harm to life on Earth is very, very remote. Most of the stars have been observed that are roughly the same size and temperature as the sun, but are younger, tend to rotate faster, are more active, with larger flares. And there are other classes of stars like red dwarfs that produce a lot of flares as well. They tend to be fully convective. In other words, the material in the star is moving around from the center to the surface and back again constantly. And these tend to be a lot more magnetically active and thus generate a lot more flares, a lot more powerful flares. So the probability of finding an inhabited planet around a red dwarf star is pretty low because, again, these flares produce a lot of UV and X-rays, but tend to strip the atmosphere off planets. And the probability of life around those would be rather small. The big worry, though, would be the possible economic impacts caused by large solar flares. Particularly, we have a lot of satellites in orbit. A lot of our economic activity depends on communication, particularly through these satellites. And also, our power grids are very susceptible to geomagnetic activity. So, a strong enough storm could actually knock out power grids. This did happen back in the 90s in Canada. A geomagnetic storm knocked out part of the power grid up there, and that again can affect our economic activity and could lead to a lot of problems. Probably not any type of civilization-ending event, though, or even world-ending event. So again, probably don't need to worry so much about these. Nearby supernova, though, can be something of a concern. Uh, Basically, what a supernova is, it's a star that explodes. There are two types. There are one's called core collapse supernovae, and there are others that are called type 1 supernovae, which are caused by the thermonuclear detonation of white dwarf stars. If they're within 1,000 light years of Earth, they can be hazardous. The blast would strip away the ozone layer and probably damage the biosphere, might even collapse the food chain, uh, and cause droughts and other types of issues like that. So they can be quite destructive if close enough. There is geological evidence this may have occurred in the past, at least the possibility of a supernova in the last 5 million years or so was found nearby. There was an excess of a particular isotope of iron that was found in a core sample in the Pacific that indicated the possibility of a nearby supernova. However, there's no mass extinction events that have been directly linked to supernovae. So again, probably the worst case scenario with these would be stripping away any protection we have from the intense ultraviolet radiation of the sun and damaging the biosphere and the food chain, things like that. This GIF image right up here just is an example of one. This was one from 2018 in a galaxy called NGC 2525, by the way. Subclass of these, though, called gamma ray burst, and these are caused by a massive star collapsing and forming a black hole, and the material of the star forms an accretion disk around the black hole and produces this jet of material at relativistic speeds. And as the jet expands, it'll collide with material that previously was ejected by the star earlier in its life and generate these beams of gamma rays, or called gamma ray bursts. And these are very energetic events, and they are observed every day. They occur in galaxies millions and billions of light years away. However, if one ever occurred within a range of about 8,500 light years, they could produce a devastating effect to the planet, in particular the Earth's atmosphere. The beam would be powerful enough to strip the atmosphere away from the planet, which would classify as a world-ending event. We would have short warning of this, by the way. We wouldn't see the actual supernova if this went off nearby. what we would see would be a brief burst of neutrinos a few minutes before the gamma ray burst hit us. So that would be the only forewarning we would really have, would be some of these neutrino detectors we have around the world would see a sudden excess of neutrino events, and then the gamma ray burst would hit us a few minutes later. Because neutrinos travel nearly the speed of light, the gamma ray burst would take time to work its way through the star and into this material, so there'd be a slight delay between the arrival of the neutrinos and the gamma rays. There's one star that is of concern that could produce the gamma ray burst I just described. It's called WR104. It's located in the constellation Sagittarius at 8,400 light years away. The primary star is what's called a Wolf-Rayet star, and it's orbiting a main sequence B-type star. And that's what you're seeing here is the main sequence star. The radiation from the Wolf-Rayet star is stripping away material as it orbits the star. And we're pretty much lined up right in the center of the bullseye, as it were, of the system. So if the gamma ray burst happened, this Wolf-Rayet star collapsed, produced the gamma ray burst, we may well be directly in the beam of the gamma rays from the star, right at the edge of the predicted danger zone. So quite possibly the worst would happen, again, would just damage our atmosphere, not completely strip it off, but damage it, damage the ozone layer, and again, subject us to a lot of UV radiation for many, many years, damaging crops, things like that. So this will be one that we should keep an eye on. Kind of a far-fetched one is stars colliding with the Earth. I recently watched this again. Anyone remember this old movie, disaster movie? It's basically, the premise is that a red dwarf star and its companion planet is discovered hurtling towards Earth, and they tried to build a rocket to flee the Earth before it's destroyed and get to this other planet that's orbiting this red dwarf star. And it's a star that actually collides with the Earth, not the planet, thus destroying the Earth. So it's an interesting movie. I actually watched this again the other night. But the chances of this happening are exceedingly unlikely. What most likely is going to happen are just close passages of stars. Here are a few examples that we've been able to work out as far as their motion, relative motions to our sun, how close these particular stars will pass. There's only one that's concerning, GL 710, which in a little over a million years may actually pass through the outer part of the Oort cloud. And the Oort cloud is basically a reservoir of comets that are about a light year to 2 light years out that surround the sun. It's the source of most of the very long period comets. Past examples, Comet Hale-Bopp was one of these comets. But a star like this passing through the Oort cloud might kick thousands of these things into the inner solar system, and over the course of decades, every night the sky would be filled with comets, and eventually one of those things might impact the Earth. So, but again, it's not something we have to worry about in the immediate future. What's a million years? A subset of this would be black hole encounters. Here's a simulation of what would happen if the Earth encountered a one solar mass black hole. But again, the chances of this are exceedingly small happening. The nearest known black hole to us is hundreds of light years away. There's no indication of anyone within our local neighborhood. They would show up in X-ray satellites, X-ray surveys, things like that. So we're probably relatively safe from black holes, at least for the immediate future. However, in about 4 billion years or so, the Milky Way and the Andromeda Galaxy are due to merge together. And each one of those galaxies has supermassive black holes in their centers that will eventually merge together after the galaxies merge. And depending where we are in our orbit through the Milky Way, we could either be scattered into the center and eventually fall into the massive black hole that's formed in the center. But more likely, simulations indicate we probably would be kicked out in one of these tidal streams and become just some star wandering in intergalactic space. So probably not even bound to the galaxies after they merge. So again, so it probably won't occur until either the sun's gone or soon thereof. This scenario is probably the one, I wouldn't even use probably, it is the one that's going to be the world ending scenario for us. And that is the evolution of the sun. The sun is a star and stars evolve. Over time, the sun is slowly getting brighter and getting bigger. In about 500 million years, the habitable zone is going to be pushed out. It's actually expanding over time. And eventually we're going to be pushed out of the habitable zone in about 500 million years. Then the Earth will experience what's called a runaway greenhouse effect. The oceans will boil off, and eventually the atmosphere will as well. And in a few billion years, the sun's going to swell into a red giant. And depending on the details of stellar evolution, stellar physics, will either wind up being engulfed in the red giant or just orbiting outside in the atmosphere. By that time, the Earth will be nothing but a cinder anyways, and will slowly spiral in and be consumed into the dying fires of the sun. And the habitable zone will be out towards where the giant planets are right now, Jupiter and Saturn. So if there's any resemblance of the human species at this time, probably have to migrate out to the moons of Jupiter or Saturn to survive. Within a few million years, tens of millions of years of this happening, the sun's going to start running out of its fuel. There's going to be a few bursts of energy that's going to pop out the outer layers and blow a big bubble around itself and form something called a planetary nebula. Nothing to do with planets other than in early telescopes, when these were discovered, they looked like kind of ghostly images of planets. That's what they were called that. But it turns out that the shape of the planetary nebula might depend on if there are planets in the system or not. In the case of our solar system, it's most likely that at least the cores of Jupiter and Saturn will survive and influence the shape of the planetary nebula that's formed by our star, and will become one of these bipolar type planetary nebulas like we see here. And then the cold, dead core of our star, the leftover remnant called a white dwarf, which is basically the core of the star supported by something called electron degeneracy pressure. Literally the electrons, by something called the Pauli exclusion principle, are balancing the force of gravity, keeping the star from collapsing further. And this thing is about 100,000 degrees on its surface, and it emits a lot of UV light, and it's going to energize that surrounding gas and light it up like a big fluorescent light bulb. That's what makes these things glow, is basically the energy from these white dwarf stars ionize the gas, excite the electrons, and make the gas glow. So this is going to be the truly world-ending event for the Earth. Right? And you have to look for that in about 5 billion years or so. So, all right, what about the universe, though? You know, is it eternal as they thought before? And if not, how will the universe end? Well, once again, we need to go a little bit back to the beginning to try to understand this. And I'm going to just kind of gloss over some things here, just give you kind of the highlights, hit the highlights, and just give you a general picture of where we are and where that will lead to our understanding of the future fate of the universe. So I'll start with this gentleman here, Einstein, and his theory of general relativity. And I gave a talk previously on this, his development of it and what it is. I believe the club has it up on their website or the YouTube page or something like that. You can go watch that if you want. I'll briefly explain what it is. And it's basically Einstein's unifying theory of gravity, that masses bend space, in this case space-time, influences both space and time, and space-time influences matter, tells matter how to move. Right? It does things, gravity does things like slow clocks down near massive objects. Rulers are shorter, things like that. That's all part of general relativity. Well, when Einstein had developed it, published it, he got to thinking about it a little bit and realized there were some consequences to his idea. And his field equations implied the universe was either expanding or contracting. Let me take a drink here real quick. So, he was a steady stater. He believed the universe was eternal and was unchanging. And you have to think about what the state of astronomy and science was at the time. At this time, the universe consisted of the Milky Way galaxy. And all the stars in the galaxy, though they appeared to be moving in random directions, didn't seem to be generally contracting or expanding. And there was no bulk motion in that regard of stars in the galaxy. So it seemed like the universe was static, steady. Now, some people suspected these other things they observed called spiral nebulae, and the more primitive telescopes at the time, some people thought these were extragalactic. They thought they were other island universes in their own right. Just they were so far away we couldn't resolve the stars in them. But most people thought they were fitting the Laplacian idea of planetary formation. They thought these were actually planetary systems in the process of forming. So the prevailing hypothesis was the universe was static. And to reconcile this in his equations, Einstein added a term to his field equation called the cosmological constant. And this would act to stabilize the universe, basically, to not have it contracting or expanding. Well, enter a guy with a lot of money and a big telescope, Edwin Hubble, and using his telescopes, he was able to resolve stars in these other spiral nebulae, these other galaxies, that, as they became called. And chiefly among them, he was able to discover a particular type of variable star called a Cepheid variable as a relationship between this change of brightness and the period of that change in brightness. And you could use that to determine distances. And he showed that these things were indeed very far away outside the Milky Way. So they were island universes in their own right. And also he was able to collect spectra of these faraway nebulae and measuring certain wavelengths of light in those spectra, particularly that like of hydrogen, the emission lines of hydrogen, and so forth, was able to measure the motion of these galaxies. He was able to show that most of them were moving away from it. And in fact, the further away they were, the faster they were moving away. It became known as Hubble's law, and it led to the idea of the expansion of the universe. They said the universe was expanding. Einstein eventually came around and realized that, well, his cosmological constant turned out to be a blunder or mistake. So he moved it from his equation, and Hubble was hailed having discovered the expansion of the universe. This led to this gentleman here, George Latour. I'm pronouncing it wrong. I've checked; it's pronounced many different ways, as close as I can come to it. He's often called the father of the Big Bang. He developed a theory called the cosmic atom that, well, if you run the clock backwards in the expansion, everything was very close together, and probably thought that the universe was created by the explosion of a cosmic atom. The idea was later expanded upon by a guy named Hans Bethe, and he developed a model called the hot Big Bang model because, well, if you collapse all the matter together, run the clock backwards, everything's close together, it's going to get hotter and denser. So as a consequence, as the universe would expand, we theorized there should be leftover radiation from this. And this idea was later mockingly referred to by Fred Hoyle as the Big Bang. It was later in the 60s. Well, first, here's a quick simulation that shows what we're talking about. The universe started hotter and dense, and then as it expanded, cooled, and areas that were denser would contract under gravity to form the structures we see today, such as galaxies. But anyways, in the 60s, the cosmic microwave background, which is the leftover radiation from the Big Bang, was discovered, and it later got the folks who discovered the Nobel Prize. So, okay, again, great. How it started, how's it going to end? Well, possibilities of the fate of the universe depend on something, actually depends on three things, that is the geometry of the universe. And there are three possible geometries. Okay? The diagram here is a two-dimensional representation of that, projected in three dimensions, but still just realize this is two-dimensional. And it's just to illustrate how the geometries actually would work if you expand it into our four-dimensional space of space and time. A closed universe would have positive curvature, like this sphere here. And the implications of it would be triangles, for example, here would actually have angles that would sum larger than 180 degrees. Right? It wouldn't be Euclidean, in other words. So if the universe had positive curvature, if you stretch out a large enough triangle and you measure the angles, you would notice that the angles actually sum to higher than 180 degrees. Flat universe, or called a Euclidean universe, is where 180 degrees. Pythagorean's theorem holds, things like that. An open universe would have negative curvature, and the sums of the angles would be less than 180 degrees. So you have to do some very long baseline measurements to be able to determine it. There actually are ways that we can do this, and I'll go into those in a moment. So what are the possible endings based on whatever the
Don, just a quick thing. Could you get a little closer to your microphone? Occasionally you're cutting out, so we'd like to hear some words are dropping. So just to let you
Okay,
know.
how's this?
That's great.
Okay. So what are the possible endings? And as I said, basically it depends on which one of these particular geometries pans out to be true. But the first would be if the universe is closed. All right, if it had positive curvature, we would undergo what's called a big crunch. Basically, the universe would currently is expanding, but eventually that expansion would slow down, stop, and then reverse itself and contract. And a sub idea would be that if it did contract all the way, maybe we would get another big bang in kind of a cycle of expansion and contraction. This is often called the big bounce. Or a cyclic universe. Okay. Another possibility is the universe is flat, would be called the big freeze. And this is where the expansion basically continues forever at a slower and slower rate as time goes on. In other words, the mass and gravity will slowly bring the expansion down to a crawl, but it will continue on forever because there's just not enough mass or gravity to completely stop it, but enough to slow it down over time. If the universe is open, it could lead to what's called a big rip. Not only does the universe continue to expand forever, but the expansion it actually accelerates, and accelerates to a rate to where eventually it starts to rip galaxies apart, and then rip solar systems apart, and then rip stars and planets apart, and eventually even atoms will be torn apart and lead to something called the big rip. Whether or not that leads to another big bang or not is still kind of an open question, but that's the possible fate if you have an open universe. Now, there's a fourth possibility that doesn't necessarily care about the geometry, at least not maybe initially. And this one's my favorite. Actually, it's called the big slurp. And what is that exactly? Well, this is related to the Higgs mechanism. You may have heard a few years back, they discovered a particle called the Higgs particle. It's associated with the Higgs field. And what the idea is, the universe is permeated by a field called the Higgs field, and how certain particles react to it determines their mass. For example, quarks, which make protons and neutrons strongly interact with the Higgs field. Thus, they have very high mass. Electrons and related particles don't interact strongly with the Higgs field. Thus, they have smaller mass. And things like photons, which don't interact at all with the Higgs field, have no mass whatsoever. Most fields, the universe is permeated by a lot of different kinds of fields, not just the Higgs field. There's also the electromagnetic field as well, and gravitational field, that all have possibly associated particles with them. The gravitational field possibly has something called a graviton associated with it, but there's no experimental evidence for that yet. But the electromagnetic field, of course, has the photon and WZ bosons. Here's what's called the standard model of particle physics that shows the different kinds of particles. Most of the particles in the universe that we're familiar with are in what are called generation 1 here. Protons and neutrons are made of up and down quarks. And of course, here's the electron. And these are neutrinos here. But there are some other kinds of quarks that probably only existed early in the history of the universe during the initial moments of the Big Bang. For the first 3 minutes. There's actually a book called The First 3 Minutes. It talks a little bit about the particle physics that happened early in the universe. And then the gluon is a particle that holds these other particles together in the nucleus. And again, here's the photon. And then these all are called bosons. They are force-carrying particles, basically. These two are associated with what's called the electroweak force. And the gluons associated with what's called the strong force. And then, of course, here's the Higgs boson, again, associated with giving these particles mass, depending on how strongly they interact with the Higgs field. This was discovered, by the way, a place called CERN. It's in the border region between France and Switzerland. This is one of the detectors that detected the Higgs boson. This thing is gigantic. Here's a picture that kind of gives a scale. There's a couple little people there. This is basically the world's largest digital camera. It's basically a bunch of detectors that are similar to the detectors on a CCD chip that detect these particles from the collisions, these high-speed relativistic collisions between protons and the shower of particles that comes out. And this thing needs to be so big because these particles have such high energy and they're moving so fast, and they so weakly interact with the matter around them. So they have to build these huge detectors to be able to detect these particles. Here's data from that instrument about the discovery of the Higgs. There's this little bump right here at about 125 GeV. That's the way in particle physics we talk about mass. We measure it in terms of the energy, actually, by Einstein's E equals mc squared equation. So there was this little bump in the data, and this was actually predicted by the standard model, and they were able to confirm it. Here's another data set from a different instrument and a different team that confirms it. It's again at about 125 GeV. What that translates in terms of mass is the proton is about 1 GeV in mass. So the Higgs boson is about 125 times the mass of the proton. So, but the Higgs field itself doesn't have mass. The particle is just a manifestation of that field. Okay. So, but what does that have to do with the big slurp thing I was just talking about? Well, the Higgs field, it's basically energy, and it's at a background level of energy, but the universe tends to want to have things at the lowest energy state possible. And it turns out that space, even empty space, has these fields in them and thus has energy. In fact, even you go out in empty space, out between the galaxies where there's no real particles around, there's a lot around you still. There's, with this background energy, there are these virtual particles that are constantly popping in and out of existence that draw energy from the background, pop into existence for what's called a Planck second, or about 10 to the 43 seconds, and then annihilate themselves. So they temporarily borrow the energy from the surrounding fields, create these particles, and quickly destroy them so it doesn't violate the laws of thermodynamics in any way, because it happens on such a small time scale. Well, again, that's a lot of energy, and the universe wants to get down to a lower energy state. So the idea is that what'll happen is someplace out in the universe, as the universe expands and cools, there'll be a place where the energy will transition to a very low, even lower energy state of basically zero energy. And that's translating from what is called the false vacuum, which is what most people think of when they think vacuum, the vacuum of space. We actually call that false vacuum, to a true vacuum. And this decay, when it happens someplace spontaneously in the universe, it'll then propagate out in this bubble that'll expand at the speed of light. And as it does, it's going to consume everything in its path. And instantaneously, all the matter in the universe, everything will be destroyed. It'll basically transition to this low energy state with no mass. And so, and you won't even feel it happen because it's traveling at the speed of light. It'll just pass right through. It's like suddenly you're there, then suddenly you're not. And again, this could just happen spontaneously somewhere in the universe. It could have happened already, and the wave's on its way now. You won't be able to observe it because it's traveling at the speed of light. So we won't even see the information of this occurring until it happens. So which one is it? What's going to happen, actually? Well, I'm going to go into where we stand with the science based off the current data, the current observation, and what's going to happen. So we'll start with going back to Einstein. And it turns out that, well, he wasn't wrong about the cosmological constant. He just put it on the wrong side of the equation. And it turns out that it's a property of space itself. The universe not only is expanding, but as I'll show you, actually, it might be accelerating its expansion slightly. But anyways, it just comes down to what the critical value of this is relative to how much matter there is in the universe. So omega m is how much matter there is in the universe, and omega lambda is how much dark energy is. What we call this, by the way, now is dark energy. How much of the energy density of the universe that is. And depending on what this ratio is, will determine the fate of the universe. That's what this plot basically shows. In time, as the universe expands. Right now, we're at a place where it's really hard to tell which one of these it could possibly be. So what they've been doing is using different ways to measure the cosmological expansion, also known as the Hubble parameter. In other words, how fast things are moving away from each other. This is a couple decades worth of data sets here. And you can see the majority of them are falling right around somewhere between 70 to 75 kilometers per second per megaparsec. And a megaparsec is about 3.6 million light years. So two things that are 3.26 million light years apart are expanding probably right around 73 kilometers per second apart. And this is pretty near the critical value. Now, recently they've done some more accurate measurements of supernovae, in particular type 1a supernovae. It turns out to be very good standard candles for measuring distances and also measuring the expansion of the universe. And this recent data set kind of indicates, again, this slight acceleration in the expansion. So we're not quite a flat universe. Implies that the universe is going to expand forever. It's going to slightly accelerate in its expansion as time goes on. Not quite in a rate that would lead to a big rip, at least not right now. It's unclear if this cosmological constant is changing over time, or if it is a true constant, stays the same throughout the entire history of the universe. There's actually some observational programs going on trying to determine that. So, but where we stand right now is the universe is going to expand forever and a slightly accelerating rate. That means we're probably facing a heat death, or in other words, the big freeze that I described earlier. What does that mean exactly in terms of what's going to happen in the future of the universe? So here's how we're pretty sure it's all going to end. As I mentioned, cosmic expansion is going to continue and probably going to continue forever. And as I mentioned, we're probably falling somewhere between what's called the critical universe and the coasting universe, or the slightly accelerating universe. We're kind of in this regime right now. Again, more measurements will determine more accurately where exactly we fall. So we're currently in what's called the stellariferous era, the star formation era. That's what that means. So, and it's probably going to continue until about 10 to the 14 years. So there's enough hydrogen, gas, and stuff in the universe to probably support star formation until 10 to the 14 years from now. But that's going to decline over time. There are going to be less and less stars formed, and the stars that are formed are going to be smaller and smaller. And as the universe expands, our cosmic horizon, how far we can actually see, is actually going to shrink. Right now, given the current rate of expansion in the universe, the visible part of the universe, the things that we can see, the size of the universe is about 93 billion light years. But wait, the universe is 14.5 billion years old, and the speed of light is the speed of light. So how could it be 93 billion light years when the universe is only 14 billion years old? Well, in that 14 billion years since the universe formed, since the Big Bang, the universe has expanded. So what we're seeing now, that's 14 billion light years away, is actually over the course of 14 billion years of expansion, 93 billion light years away. That's how big the visible universe is that we can actually see. But that horizon is going to shrink over time due to the cosmic expansion. So eventually, we're only going to see our local supercluster. We're actually part of the Virgo supercluster of galaxies. We're a very distant part of it. We're about 65 million light years from the Virgo cluster, which forms the core of this cluster. And we're slowly moving towards it. Whether we'll actually get there in this time is unclear. Again, it kind of depends on the parameters of expansion and how fast it really is. But eventually we'll still lose sight of it. And even the local group, which by this time probably will just consist of, well, as we mentioned, the Milky Way and Andromeda are going to merge. Well, eventually M33 and the Magellan Clouds and a lot of the local dwarf galaxies are all going to merge together. We're just going to become one big mega galaxy. And so, but whatever else is, that would have been part of the local group can expand out of the horizon. So eventually we're just going to see the Milky Media or whatever it's called at that point in 10 to 14 years. This will be a very difficult era to do cosmology because you won't have really much else out there that you can measure the cosmic expansion with. The cosmic microwave background will have redshifted out of view, and the background temperature of the universe will be so low that it would be very difficult to get this cold enough to be able to be sensitive to the temperature of the background. It's hypothesized that maybe hypervelocity stars, these are stars that are kicked out of the galaxy by interacting with the supermassive black hole at the center or some other interaction, get kicked out of the galaxy. You might be able to measure the cosmic expansion as these things move out of the galaxy. But there might come a time when you cannot do cosmology. Then we move into what's called the degenerate era. This is basically 10 to the 14 to 10 to the 40 years. That's a 10 with 40 zeros after it, years from now. And in this era, it's going to be dominated, well, star formation is basically on the end, so there won't be any beautiful vistas like here of the Orion Nebula anymore, or any such nebula like that. Star-forming nebulas are going to become a thing of the past. New stars aren't going to be forming. galaxies are going to get redder and redder and dimmer over time as the stars get older, and most of the stars forming are red dwarf stars. So the galaxies are going to become very faint and very difficult to see. Even being inside of one, it's going to be hard to see it. And then finally, the last normal stars will die, either as supernovae or planetary nebula and things like that. So basically what's going to be left are just stellar remnants, white dwarfs, neutron stars, black holes are all that's going to be left. And of course, any planets that formed will be around as well. You might also should mention things like brown dwarfs. If they collide, they could form a new red giant star, or I mean a red dwarf star. And these things can be rather long-lived. Red dwarfs tend to live in the order of a trillion to 100 trillion years, depending on how massive they are. The smaller they are, the longer they live. So it will be a very dark universe. Any free atoms floating around will get ionized because there'll still be plenty of high energy photons in the form of gamma rays flying around the universe. But if there's any atoms around, it'll kick the electrons out of their orbit. So if it's not part of a planet or a star or something like that, it's going to get ionized. White dwarfs, they cool off. They cool off over time. Eventually the sun, which will become a white dwarf, it'll cool off to the background temperature of the universe, become what's called a black dwarf. These things will, as they cool, they'll crystallize as well, and they're often called big diamonds once they crystallize, so they might form like giant diamonds. Excuse me. Song Lucy in the Sky with Diamonds kind of thing. And then we move into what's called the black hole era, because well, that's pretty much all that's going to be left. That's 10 to the 40 to 10 to the 8 years. And basically what comes down with black holes is they evaporate. This was theorized by Hawking, called Hawking radiation. And the process involves, again, getting back to the state of the vacuum, the empty region of space near the black hole. As I mentioned, there are these virtual particles that are constantly created and destroyed. If this occurs close enough to a black hole, one of those two particles that are formed in these particle pairs will get sucked into the event horizon, and then that virtual particle that's left will become a real particle and will escape from the black hole, carrying some of the mass. And what this means is basically black holes evaporate over time. And even the largest black hole, the current largest one that I know of is one called TON 618, and it has about the mass of about 66 billion suns. It will take about 10 to the 99 years to decay. The 10 to the 108 numbers, assuming that there might be other black holes that form and merge and get bigger. But pretty much the last black hole will evaporate away in about 10 to the 8 years. What about times beyond this? Well, this is when it gets really weird and really hypothetical. One of the predictions for this is a really big number, 10 to the 10 to the 50th years. That's 10 to the 10th power to the 50th power. So it's a 10 with 10 to the 50 zeros after it. Something called a Boltzmann brain might appear out of the vacuum of space due to quantum fluctuations. This was a reductio ad absurdum argument against the paradigm of the universe's formation in apparent order, its low entropy. And Boltzmann, one of the physicists who worked in the field of thermodynamics, wondered why the universe started at such a low entropy state, higher entropy. But basically, he hypothesized that the probability of this happening would be just like a brain, the same probability as a brain just appearing out of nothing, with the memories of living in a universe like we live in now. But again, that's theoretically possible given the way quantum mechanics works and probability that such a thing could occur. If we go out to 10 to the 10 to the 76 years to 10 to the 10 to the 120 years, this is the amount of time it might take the universe to cool down enough to reach the state where this false vacuum decay would occur, the big slurp, and the universe would transition down to a lower energy state. But it's also probable that with quantum mechanics effects taken into account, that in 10 to the 10 to the 56 years, quantum fluctuations could generate another Big Bang. Now, there's only one thing that could possibly throw a wrench into our timeline here. By the way, this is, again, kind of the picture of what the universe will look like in that time frame, given what I've covered up to this point. Basically, a very dark, unique universe, but of course, there would not be anything around to observe it anyway, so it doesn't matter. But one idea that might throw a wrench in this is something called proton decay. One of the predictions of the standard model is that protons, or nucleons in general, both protons and neutrons, aren't really stable. And they possibly will decay over time. And the half-life for this is estimated to be about 10 to the 36 years. So in other words, in 10 to the 36 years, roughly half of the protons in the universe should have decayed if this idea is true. And it still, though, should be able to be observed today, even though the probability is very small that of this happening, of proton decaying happening. They're building these big detectors, hopefully, to see if there might be at least one or two that decays early, because decay is a random process. It's a quantum mechanical process. So this might be observable, and they're building instruments to try to detect this to see if they are indeed unstable as predicted. And if this is true, then pretty much all the nucleons, all the particles, protons and neutrons will have decayed by 10 to the 36 years, which will be well into the black hole era, which basically means that the universe at that point would be consist of subatomic particles called positrons and gamma rays and black holes, which the black holes would still continue to evaporate over time, and then eventually still leading to what I showed earlier. So this is pretty much how we're sure it's going to end, but it's going to be in a time long ways away that you don't need to worry about. You don't need to mark your calendars to worry about this, and that's why I don't worry about endings anymore, because this is never going to happen in my lifetime, and but it's very fun to think about. So here's a recommended reading list, by the way, if you're curious to learn more about this subject. They go into a lot more detail than I did. Some books I recommend. The first one in particular is really good, but I will now open up if anybody's got any questions or anything like that. So I'm going to stop my share, and then I should be able to see the chat. Okay, anybody got any questions? Question? The topic pretty well.
It was pretty interesting.
Slides were beautiful and interesting.
So, Don, how much evidence is there for the false vacuum idea?
Not much, but given how other types of fields behave, this is based a little bit off other types of fields in nature, the way that they tend to behave, such as atoms want to be in their ground state. They want to get to the lowest energy state possible. So they will decay and emit photons and other particles to try to get down to a lowest energy state. You heat something up, it wants to cool down to a cooler temperature. It wants to get as close to the background temperature of the universe as possible, given whatever the environment it's in. And the fact that the universe, the empty space around us is filled with energy, it only makes sense that it wants to get rid of that energy. It might be one of the things also driving the expansion. They think it might be responsible for the cosmological constant is space trying to get down to its lowest energy state and all the fields in space.
Is this an analogy to the phase transition that resulted in inflation at 10 to the negative 34th of a second or something like that?
Yeah, basically, when the Big Bang occurred, there was a brief period called inflation where there was a phase transition in the energy fields that caused the universe to expand and cool, and it expanded faster than the speed of light. It turns out that space can expand faster than the speed of light. And that's why our physical volume that we can see is the size it is. The universe probably is infinite, because literally the Big Bang happened everywhere. The cosmic atom idea, I should have been a little more clear, is wrong in that there wasn't a place that exploded. There's no center to the expansion. Everything looks like it's moving away from everything else. If you go to a planet in the Andromeda galaxy, everything is going to be moving, looks like it's moving away from you there, or any place else in the universe, it's going to look like everything else is moving away from you. And as these fields transitioned through this rapid expansion, they went to a lower energy state, and that actually allowed the Higgs field to achieve a value to where it actually gave mass to particles. It wasn't until the universe cooled down to this point that the Higgs field was able to impart that characteristic on matter. So there was actually no matter in the universe before inflation occurred.
Okay, I got one question that nobody has answered for me. We're talking about the expansion of space-time.
Yes.
And I want to know, is it just stretching, or are we actually saying that they're creating more space-time to fill in the void? In other words, the fabric of space-time itself is not stretching so much as more space is being created.
Well, that depends on the value of the cosmological constant. If the value is large, the expansion is going to accelerate, and it will actually accelerate to the point where, again, it'll start ripping everything apart, galaxies, stars, planets, and eventually even atoms, and even the particles, subatomic particles that make up atoms will be ripped apart. So yeah, basically in that regard, it is a stretching of space, but it is also the fact that there's just more space also physically being created there at the same time. So it's a little bit of both, actually.
Okay.
The thing that people have problems wrapping their brains around is that it's not expanding into anything.
Right.
Because again, the universe most likely is infinite, and this expansion is happening everywhere. And that also has some weird consequences, because there are a limited number of particles, kinds of particles, as I showed like in the standard model. That means there are only 10 to the 150 possible combinations of particles. All right, but if the universe is infinite and there are infinite number of particles, that means that the universe repeats itself in its structure periodically,
Mm-hmm.
go farther away. So literally hundreds of billions of light years away, there's another copy of me giving this exact same talk at the exact same time. And or slight variations like we all have 3 arms or something weird like that. So there are possibly many variations of ourselves out there, infinite numbers of them out there. So that's a very weird consequence of this, of our understanding of the universe. And
Oh, scary thought.
yeah, there's a whole bunch of me out there. Pretty scary. Any other questions?
Well, Don, your talks are always very detailed and well researched, and I can't find any fault with the content in terms of the accuracy that based on what my experience, and so kudos to you. Ness had to cut out to deal with some childcare issues, so I will say on behalf of her, thank you very much for giving this extremely detailed and rich and interesting talk, and hope to see you soon in person.
Yes, awesome. Looking forward to doing these programs again in person. So yeah, watch our website as far as our programming goes. Um, we've got our new Vistas talk that we're doing again on the 15th and of July, and then the Sun programs 2 Saturdays at the end of July. So please come out for those. So many folks come out and volunteer for that. It'd be appreciated. Help run a solar telescope or something. And yeah, I'm looking forward to doing this again.
Okay, well, I am going to turn off the live stream. I'm checking to see whether or not there's any questions or comments on the live stream. We had a steady trickle of folks watching on the Facebook page, so I will say goodbye to the Facebook folks. And once again, the Columbus Astronomical Society is going to be meeting in person next month, out of doors, to do the annual swap meet. So we will get to see each other there. Your advice or your discretion is asked for in terms of being in the presence of other people. If you haven't been vaccinated, please take that into consideration. Wear a mask. But if you've been vaccinated, we will be looking forward to seeing you at Perkins next month. So thank you very much, and I am going to sign off the live stream, and we're going to get to the social part of the meeting. So thank you very much.